All right, we're jumping into part 2 here. This is the really key idea here. It's essentially working backwards. Previously, we were given a complex number and we were asked to find the magnitude and find the argument, or remember the argument's a fancy way of saying the angle of that complex number's vector, right? So today's lesson really has been leading up to our ability to work backwards. If I know the magnitude and I know the argument, or the angle, can I figure out the coordinates of that specific complex number? And the answer is, of course, yes. So, I want you to actually try to tackle this because our previous examples we left off in part 1 actually are really the same thing as this, just hidden in a different format, right? So if we think of a complex number and we know that its magnitude is 2, aka its radius, right? And its argument is pi thirds, right? Its angle. Figure out an x plus yi form. Go ahead and pause now and do this yourself, and then we'll take a look at the solution. All right, let's take a look here. Hopefully you recognize that we're really asking the question converting from polar to rectangular, right? Because the magnitude's just like a radius, and the argument is the same as the angle. So essentially what we're saying is we've gone out 2 and rotated by pi thirds. So we're given the polar coordinate 2 comma pi thirds, but really what we're trying to figure out is the rectangular coordinate, but we're just leaving it in the format of a complex number. So if z is x plus yi, and you may not have done it exactly in the same way as I did as far as how you laid your steps out, but that's okay. You should essentially end up with the same thing in the end. Okay? We know x is r cosine theta. We know y is r sine theta, right? But in this case, technically it's going to be, we can think of it as the magnitude and the argument. Okay, but I'll still use r and theta. And we just simplify that out. Then we get the complex number is 1 plus square root 3i. Now there's one really key thing that's important here, and that is this connection here, okay? If I have a complex number in x plus yi form, then r cosine theta plus r sine theta I is what we call the polar form of a complex number. So let's officially jot those down now in our notes. So this brings us to a really important definition here, or pair of definitions. We already are familiar with the rectangular form of a complex number, but now polar form, we've already learned the conversions, right? Is if I have z equals x plus yi, then z can be written as r cosine theta plus r sine theta I. And notice something, this r, both of these have a factor of r, so that can be factored out. So r times cosine theta plus sine theta I. Now it is standard in this format. I don't really know why, but it is standard to put the I in front for some reason. So we'll write it as r equals cosine theta plus I sine theta. And there's actually an abbreviation that we're going to use in this class because we'll use this format a lot. And we're going to abbreviate this CIS, cosine I sine. As z equals r cis theta. So anytime I'm talking about cis theta, I just mean cosine plus I sine, okay? So that is going to be our official polar definition for a complex number. Now, one side note, just to mention, technicality here. Well, it's not a technicality, but it's just important to mention that r is the same as the magnitude of z, and theta is the same as the argument of z. So just keep in mind that r is the same as its magnitude. Theta, what we mean by that is his argument, but that we've already established that. So there we go. There is our biggest thing for this lesson. A little bit more to use these and a few questions to talk about, or things to do with this before we finish. Okay, so let's just apply directly what we just talked about. So let's be given another complex number, we'll call it w, and his magnitude is 4, and his argument is 4 pi thirds. Write it in polar form and then in rectangular form. Why do I say polar form first? Because once you write it in polar form, all you have to do is then just simplify it out further, and then you'll get it into rectangular form. So this is one that I'm fairly confident that I can ask you to do yourself now again. So if you go ahead and pause, we'll come back together and look at the solution. Okay, so let's take a look at this. Polar form is r times cosine theta plus I sine theta, right? But don't forget that r is the same as magnitude, and then the theta is, of course, the argument. So I just plug this stuff in. We simplify the cosine and sine first, and then that 4 distributes in here, right? So 4 times negative 1/2 is negative 2, and 4 times this is going to be minus 2 root 3, and then in the rectangular that I goes on the end. So here's my polar form right here, before we simplify it, and then here is my rectangular form after we simplify that, okay? So that's the basics of everything we need to know. I'm going to do one more thing with you that's going to get us thinking and looking ahead into some of the relationships that we're going to look at with this later on. So let's do that before we wrap up. All right, so we're going to consider the two complex numbers that we looked at in the previous two problems, z and w. And I've taken the liberty of putting down both the polar and the rectangular form of each one of those. But we want to find the product z times w in both polar and rectangular forms. If I just only started with polar form and I want to figure out that product, you can probably tell that all the distribution stuff you had to do would be a little bit crazy to keep track of. You might agree with me, at least at this point right now, that if we use the rectangular form, that'd be an easier product to find. So let's just start with that in rectangular form and say z times w is going to be 1 plus root 3i times negative 2 minus 2 root 3i. Okay? And this is one where I'll have you pause right now again and work that out, the product, just to get more practice. Okay, so I've just written the first line of steps here. So this, 1 times negative 2 gives me negative 2. And then 1 times negative 2 root 3i is another negative 2 root 3i. And then I have root 3i times negative 2, which gives me actually the same thing, another negative 2 root 3i. And then root 3i times negative 2 root 3i. Don't forget, these root 3's, root 3 times root 3 by definition is just 3, right? So this just becomes 2 times 3, which will make 6. And I made one mistake here, didn't I? This has to be I squared. And we remember that I squared is the same as negative 1, right? So let's put some stuff together. This becomes negative 2. These i's can combine to minus 4 root 3i. I squared is negative 1, and so I get negative 6 times negative 1 becomes a plus 6. So in the end, negative 2 plus 6 is 4. So I have 4 minus 4 root 3i. So there's the product in rectangular form. How do we get this in polar form? Well, wait a minute. We did do some conversions in part 1 of this lesson, right? If I have the x and the y, I can convert it back. So let's go ahead and... So here's the work for converting it. And again, remember, we just used our conversions from before. But in this case, we know the x and the y, right? 4 and negative 4 pi thirds. And if I just put those into my conversions that we talked about, then r simplifies and becomes 8, exactly 8. And then the theta, this one's tricky because remember, this complex number here is in quadrant 4. So we've seen that we need to subtract from 360, but in this case we're in radians, so 2 pi. So in the end, if I do the tangent inverse, this is actually really interesting because negative 4 root 3 over 4 simplifies to negative root 3, and that has an exact angle on the unit circle. It's negative 60 degrees, but in radians that's negative pi thirds. And remember, negative pi thirds is the same as positive 5 pi thirds if we write the standard angle. So my theta is 5 pi over 3. So here's our summary. Z times W in rectangular form is 4 minus 4 root 3i, and we knew how to work with that with complex numbers. but there's something special going on actually that we're leading to here for the polar form. Look really carefully at the two radii here, 2 and 4, and what the new radius is, and look very carefully what our original arguments were, our original angles, pi-thirds and 4 pi-thirds. And our new angle involved here is 5 pi-thirds. We're not going to formalize this at all right now, but just to get your mind thinking and those wheels spinning here as we move forward to things we're going to do in the future. That is it for this lesson, and so I want to say, again, happy math, and we'll see you next lesson.